Hey there. Today we're going to look at something cool in maths and physics called spherical harmonics and how they can be used to create any desired pattern on the surface of a sphere. Spherical harmonics are a special set of waves that can be used, among many other things, to describe the vibrations on the surface of a kicked ball or the quantum mechanical angular dependence of electron orbitals in an atom. Think of spherical harmonics like the ingredients in a cookbook. Just like you can mix primary colors to create any other color you want, you can combine spherical harmonics to represent any pattern on a sphere's surface. That's just a taste of what spherical harmonics are all about. But in order to understand spherical harmonics more quantitatively, let's first take a dimensional step back and start with vibrations on a one-dimensional string. A plucked guitar string causes the body of the guitar to vibrate at integer multiples of the lowest frequency, which is defined by a wavelength that is twice the length of that vibrating string. That there is more than one frequency is actually what gives a guitar its characteristic timbre. Indeed, the sum of all the different vibrational modes of any musical instrument is what makes that instrument recognizable. So on our journey to vibrations on the two-dimensional surface of a sphere, we now make a stopover by considering what the consequences are of closing the string to form a loop. We see that those strings that vibrate with odd numbers of half wavelengths now, as loops, have a kink or abrupt change in angle where the two ends of the string joined. This is physically unreasonable and is therefore forbidden. The take-home message is that only those loops created from strings that vibrate with even numbers of half wavelengths are allowed. Analogously, the spherical harmonics on the surface of a sphere must be smooth functions with no abrupt changes, and as such must vibrate with integer numbers of waves both in the polar direction theta and in the azimuthal direction phi. They're labelled mathematically as YLM. Shown here is the Y74 harmonic. Note that the blue regions have the opposite vibrational amplitudes to the red regions. When the blue regions breathe out, the reds breathe in and vice versa. The white lines are nodes where the vibrational amplitude is 0. The integer L determines how many nodes there are in total. M is equal to the number of longitudinal nodes and thus the number of wavelengths in the azimuthal direction. There are therefore L minus M horizontal or latitudinal nodal planes. In this gallery of all the spherical harmonics up to L equals 8, we can identify some more of their features. First, the number of spherical harmonics for a given M is equal to 2L plus 1, spanning from M equals minus L to M equals plus L. Note that for M equals 0, there are no longitudinal nodes. The precise equation describing a given YLM is shown here for the more mathematically bent, though we need not concern ourselves here with this. The complex exponent e to the im phi can be decomposed into real and imaginary components, cos m phi plus I sine m phi. Here we see the real components, which for a given L are symmetric around m equals 0 for even m and antisymmetric for odd m. The opposite is true for the imaginary components shown here. We now embark on a mathematical culinary journey. You should at least intuitively by now know what spherical harmonics are. Now here comes the central message of the maths part of this video. In our culinary analogy, given a precise recipe of ingredients, we can generate any image on the surface of a sphere by their combination. The raw ingredients are thus the spherical harmonics, The amount of each that we need is given by the recipe, and the final spherical harmonic bun is the resulting image. Mathematically, our spherical harmonic bun is a sum from L equals 0 to infinity and m equals minus L to plus L of each and every YLM, whereby the amount of each that we need is defined by a weight given by CLM. In practice, we stop adding more ingredients after a certain value L max, so in our cooking metaphor, adding more and more small amounts of spices at some point adds little to the taste of the final bun. But importantly, we need to now know just how much of each ingredient we need. We turn to this now. The equation to determine each coefficient CLM is given here. It might look complicated at first blush, but graphically we see it really isn't so foreboding. The integrand term f theta phi times YLM theta phi star, whereby the star represents a complex conjugate of YLM, is simply the scalar multiple of the spherical image we want to create with YLM star. We then integrate this over the entire spherical surface, and that's it. Note that the sine theta term is needed because we are integrating in polar coordinates. We need to perform this integral for each and every YLM. But once this is done, we can plug these into our recipe for our bun, and we should get a perfect bread roll. Okay, let's now look at a real-world example, literally. We add batches of 2L+1 YLMs, one after the other, for every increase in L by 1. As we do so, the features become less blobby and increasingly detailed. Let's pause at L equals 10, by which time we've summed 121 spherical harmonics, each weighted by its individual CLM coefficient. Okay, let's add a few more and pause again at L equals 20. I'm guessing that for most of you things are beginning to look pretty familiar, though admittedly one feature towards the bottom does look more like a fidget spinner than anything else. By L equals 50, the global picture is clear, so to speak. Nonetheless, let's continue. I decided to cut my losses at L equals 720, as this is increasingly a game of diminishing returns. Each new L requires 2L+1 weighted harmonics, but the fineness or resolution improves only as L divided by L+1, which for large L is a very small improvement indeed. The resolution of any image created by spherical harmonics has an angular value in radians of pi divided by L max. Given L max is equal to 720 and the radius of the Earth is 6,378 kilometers, we obtain a resolution of 28 kilometers. As such, the island of Malta, due south of Sicily, is just about resolved. Okay, that's enough chit-chat from me. The second part largely speaks for itself, the geology of planet Earth.